the rate constant is proportional to e raised to minus Ea by RT at the given temperature T. The minimum energy required for the reactants to form activated complex is called as activation energy. So what was the Arrhenius equation? It is K is equal to A into e raised to minus Ea by RT. This was the Arrhenius equation. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry, Vidhyaashram School of Excellence, Mysore. So today we are back with session 5 of the chapter Chemical Kinetics. So in last session, we studied about the half-life of a reaction. Yes, what is half-life of a reaction and the equation to calculate the half-life of a first order reaction as well as a zero order reaction, and we did the numericals as well. Right. Now, then we also studied about what is a pseudo first order reaction, and then we did some numericals as well. So let's see what we are going to study in today's session. Yes, the temperature dependence of rate of a reaction. Okay. So how does the rate of a reaction depend upon the temperature? So till now we were studying about the effect of concentration on the rate of the reaction. We studied the rate law, what is first order, second order, zero order, all those things, which was the relationship or the dependence of rate of the reaction and concentration. Now we are going to study how the temperature depends upon the rate of the reaction, right? And then we are going to study about one very important equation that is called as Arrhenius equation, right? And what is activation energy, and also the qualitative increase in reaction rate with temperature. Okay, that is how you can qualitatively express it. So all this we are going to study in this session. So first of all, the temperature dependence of the rate of the reaction. So what you have to understand is when the temperature is increased, okay, when the temperature increases, the rate of the reaction also increases. So as you can see here, the rate of a chemical reaction is significantly affected by change in temperature. For most of the chemical reaction, for most of it, the rate will increase with increase in temperature. Okay, so the rate will increase with increase in temperature. So the ratio of the specific rate constant of the reaction at two different temperatures differing by 10 degrees Celsius is known as temperature coefficient. Okay, so if you are increasing the temperature by 10 degrees Celsius and the ratio of the specific rate constant of the reaction, once this temperature increased by 10 degrees Celsius is called as the temperature coefficient. So the rate usually becomes doubled for each 10 degree rise in temperature. So generally you can say whenever there is a 10 degree rise in temperature, so let's take initially the temperature was T, and now the temperature is increased to 10 plus 10 degrees Celsius. 10 degrees Celsius is increased. So what happens to the rate of the reaction? The rate of the reaction will be doubled. Right, the rate of the reaction will be doubled. So the ratio of the specific rate constant for 10 degrees Celsius rise and the initial temperature will give you the temperature coefficient. Okay, so it will be Kt plus 10 degrees Celsius increase divided by Kt. So that is called as the temperature coefficient. So what you have to remember, when the temperature increases, the rate of the reaction also increases, and for every 10 degree Celsius rise in temperature, the rate of the reaction increases by double. Okay, so now we are going to study very important equation, that is Arrhenius equation, which is an equation which gives a relationship between the rate of the reaction and how it depends on temperature. So let's see, according to Arrhenius reaction, the rate constant is proportional to e raised to minus Ea by RT at the given temperature T. So this is a very important equation, that is K is equal to A into e raised to minus Ea by RT. So according to Arrhenius equation, according to Arrhenius, what did he say? The rate constant of a particular reaction will be directly proportional to e to the power minus Ea by RT. Okay, so we'll study all the terms one by one now. Okay, so now to remove the proportionality, what do? We introduce a constant here. So the constant used is A here. That is K is equal to A into E raised to minus EA by RT. So this minus EA by RT is in the power. Okay, so this equation is called as the Arrhenius equation. So it gives a relationship between the rate constant and temperature. Okay, so I hope it is clear. So now let's see each one of the terms in this reaction. So what is K? We already know what is K. K is called as the rate constant. Okay, now A is a constant which is here. The constant name is Arrhenius constant. Okay, it is Arrhenius equation. So it is Arrhenius constant, or you can also call it as frequency factor. Okay, so if the question comes to find out the Arrhenius factor or frequency factor, what is it that you have to calculate? It is A. Okay, now E raised to minus EA. Now what is EA? EA is the energy of activation or activation energy. So now what is activation energy? We'll study in the upcoming slide. So as of now, EA is the energy of activation, or else you can also call it as activation energy. Now R and T are already familiar for you. R is the universal gas constant and T will be the temperature in Kelvin scale, in SI unit, that is temperature in Kelvin scale. So this equation is very important, which is called as the Arrhenius equation. Again, it gives a relationship between the rate constant and temperature. K is equal to A into E raised to minus EA by RT. K is the rate constant, A is the frequency factor or Arrhenius constant, EA is the activation energy, R is universal gas constant, and T is temperature. Okay, so the minimum energy required for the reactants to form activated complex is called as activation energy. Okay, so what is activation energy? Now we are going to see. Okay, so we already know that. Let's take, there is a reactant R and it forms product P. So we know that reactants combine and they get used up and then they finally form the products. So if the reactants have to combine or the reactants have to collide with each other and form the product, they must be first forming a complex which is called as an activated complex. So the reactants directly do not form the products. Reactants first will form an activated complex, and once the activated complex is formed, which is an intermediate state which is very unstable, and it forms the product. Okay, so the energy which is required by the reactants to collide with each other and form the activated complex is called as the activation energy. Okay, so the minimum energy required for the reactants to form the activated complex is called as activation energy. So once this activated complex is formed, further the product will form. So the energy which is required for the reactants to collide with each other and form the activated complex. Okay, activated complex is called as activation energy. Okay, now activation energy will be equal to threshold energy minus the average energy possessed by the reactant molecules. Now what is threshold energy then? It is the minimum amount of energy the reactant must possess to form the products upon mutual collision is called as threshold energy. Okay, so threshold energy is the minimum energy which is required by the reactants so that they will undergo effective collisions. So I hope what is activation energy is also clear, right? So now let's consider the reaction H2 plus I2 is giving 2HI. So what is actually happening here? See, H2 is shown here. There is a single bond between two hydrogen, H2 and I2. So these are the reactants H2 and I2 which is shown here. Now what happens is they once start colliding with each other, they form an intermediate state which is called as the activated complex, right? It forms an intermediate state in which, yes, as you can see, this H and H bond will start breaking and H and I bond will start forming. Okay, so the hydrogen-hydrogen bonds is not completely broken and hydrogen-iodine bond is not completely formed. That is why it is shown by a dotted lines. So it is an intermediate state wherein which the breakage as well as forming of the bonds is happening. So what is the product which is formed here? HI, right? 2 molecules of HI. 2 moles of HI. So what will happen? This bond should break and hydrogen-iodine bond should form. Okay, so this is called as an intermediate state. After the intermediate state, the 2 molecules of HI will be formed. So this is how the reactions proceeds. So first the reactants will start colliding. It will form an intermediate state. Thereby it will form the products. Okay, so according to Arrhenius, this reaction can take place only when a molecule of hydrogen and molecule of iodine collide to form an unstable intermediate. So what happens? H2 and I2 will collide, form an intermediate. Okay, it exists for a very short time and then breaks up to form 2 molecules of hydrogen iodide. Okay, so this intermediate state is very unstable. So very unstable means it can't stay in that form for a long time. Immediately the bonds will break and start forming, and what happened? Yes, you will get 2 molecules of hydrogen iodide, HI. Okay, the energy required to form this intermediate, which is called as the activated complex, is known as activation energy. Okay, so we have already studied that the energy which is required for the reactants to form this particular intermediate is called as the activation energy, which is EA. So now let's understand the graph here. So if we plot a graph between potential energy and reaction coordinate, let us understand how the graph is. Okay, so this particular point A, as you can see, here is the reactants initially where it is present. So which is the reactions here? H2 and I2. We are considering the same reaction. So what happens? H2 and I2 will be the reactants. That will be here. So now what was activation energy? Activation energy is the energy required for the reactants to form the activated complex. So what happens? The reactants will start colliding with each other and finally form the activated complex, which is very unstable, right? So the energy which is required for reactants to form activated complex is called as activation energy. So this much will be your activation energy, right? From the reactants to the activated complex, how much energy? That is the activation energy. Now what happens? Once this unstable intermediate is formed, activated complex is formed, immediately product will be formed. So what happens? Now directly the product will be formed. Okay, and the product, as you can see, 2HI will be formed here. So now you can observe one more thing here. The reactants are placed little above in this graph than the products. The reactants is here, products is here. Now why it is like that? The reactants are having higher energy and lesser stability. Okay, higher energy means what? Less stability. Energy and stability is always inversely proportional. So when higher energy, see, it is potential energy here, right? So higher energy, less stable. Now once it is forming the product, what happens? It is having lower energy because it is more stable. That is why the reactants is shown here and the products is shown here. Okay, so lesser energy and more stable will be the products. So I hope the graph of activation energy and activated complex is also clear for you, right? Okay, now moving on to the next part, that is qualitative increase in reaction rate with temperature. Okay, so all the molecules in the reacting species do not have the same kinetic energy. Okay, so you should not be thinking that all the molecules in a reaction will have the same kinetic energy or they will possess the same energy. So different molecules will have different kinetic energy. So Ludwig and James Clerk Maxwell used statistics to predict the behavior of large number of molecules. According to them, the distribution of kinetic energy may be described by plotting the graph between Ne by Nt with a given kinetic energy. Okay, so if we plot a graph between the fraction of molecules and the kinetic energy, we can understand that most of the particles which energy they will possess. So let's see here, Ne is the number of molecules with energy E and Nt is the total number of molecules. Okay, so if we plot a graph between the fraction of the molecules and kinetic energy, okay, we'll get a graph like this. Okay, and as you can see, the graph starts increasing and it suddenly decreases. So at this point, this is the highest point in which shows the most probable energy or most probable kinetic energy of the molecules. So as I said, the molecules will not have the same energy. All the molecules will not have the same kinetic energy. See, it will increase. Certain will have only very less kinetic energy. Certain will have little more high kinetic energy. But most of the particles will have a higher kinetic energy, which is called as the most probable kinetic energy. That is the maximum number of molecules, which energy it is possessing, that is called as most probable kinetic energy. So now the peak of the curve corresponds to the most probable kinetic energy, that is the kinetic energy of maximum fraction of molecules. Okay, so if we plot a graph between fraction of molecules and kinetic energy, we'll get a peak in the curve. That peak will represent the kinetic energy possessed by the maximum number of molecules. So I hope it is clear. So now we are going to see a figure here. Okay, let's see this graph also. The following figure shows the energy distribution curves at two temperatures. Okay, that is T plus 10 and T. That means if you are increasing the temperature by 10 degrees Celsius and before that. So we are plotting two graphs now. Okay, so at temperature T, the fraction of molecules possess kinetic energy greater than or equal to the activation energy and is capable of making effective collisions. So let's see what is happening when we are increasing the temperature now. Okay, so we already studied the graph of fraction of molecules and kinetic energy and most probable kinetic energy. Now we are going to see in the same condition, we are going to increase the temperature. Now what happens? Okay, so let's see. As the temperature increases from T to T plus 10 degree, the fraction of molecules having kinetic energy greater than the activation energy increases. Okay, so the activation energy increases. Thus, effective collisions and hence the rate of reaction also increases. So, if the reactants have to form the products, effective collisions must take place. So, what happens when we are increasing the temperature? The kinetic energy also increases. Kinetic energy increases, hence the effective collision increases. Hence, what happens? More number of particles is getting the more kinetic energy. Okay, so the fraction of molecules having more kinetic energy is increasing, hence more effective collisions and the reaction rate also will increase. Thus, an increase in temperature increases the number of effective collisions, hence we can also say that in turn it increases the rate of the reaction. So, in general or in conclusion, we can say that when the temperature is increased, okay, what happens? Yes, the kinetic energy increases, effective collision also increases, hence the rate of a reaction also increases. Now let's see the same graph, the fraction of molecules and kinetic energy. So this particular graph you can see that was for T degree. Okay, T, the temperature T. Now the second graph you can see that is for T plus 10 degree. So as you can see, only this many fractions, only this much portion was for the temperature T. Now, if we increase the temperature by T plus 10, see, this much, the gray portion you can see, that much portion or that much fraction of molecules is having the minimum activation energy. So, what is happening here? When the temperature is increased, the fraction of molecules attaining the activation energy is more, hence more effective collisions, hence the products will be formed easily. Okay, hence what we can say in general, hence the temperature increases, the rate of the reaction also increases. So I hope the relationship or the dependence of temperature and rate of reaction is clear for you. Hence the Arrhenius equation is a very, very important equation. So now let's see. So now let's move on to the next part where we are going to find out in which all methods we can calculate the energy of activation or activation energy. So first one is graphical method. In the Arrhenius equation, the factor e raised to minus Ea by RT corresponds to the fraction of molecules that have kinetic energy greater than the activation energy. Taking natural logarithm on both sides of the equation, we'll get this. So what was the Arrhenius equation? It is k is equal to a into e raised to minus ea by rt. This was the Arrhenius equation. So now we are taking the logarithms on both sides. We are taking ln on both sides. So what happens? Ln k will be equal to ln a. See, ln k will be equal to ln a plus, okay, ln a plus e raised to minus ea by rt is there. So if we are taking ln of e raised to minus ea by rt, only this will remain. Okay, so the e won't be there. So what happens? Ln k will be equal to minus ea by rt. The power will come. Okay, so the minus ea by rt plus ln a. Okay, so this will be the equation. Now what we are going to do? We are going to plot a graph between ln k versus 1 by t. Ln k versus 1 by t, and it will give a straight line. So as you can see, if we plot a graph between ln k versus 1 by t, we'll get a straight line here, and the slope will be minus ea by r. So from the slope, we can calculate the activation energy. Okay, so the slope of this line is equal to minus ea by r, and the intercept will be ln a. Okay, so where this point, the graph is joining to the y-axis, the point will be the intercept, that is ln a. Okay, now hence by measuring the slope, the activation energy can be calculated. So once we take the logarithms, we obtain this equation. Now we are plotting a graph between ln k and 1 by t. We obtain a graph like this, which is a straight line, and from the slope, what is the slope here? Minus ea by r. So how did we obtain this? Just by seeing this equation and comparing it with y is equal to mx plus v, we can say. So what is y? Ln k. What is x here? 1 by t. And what is c here? Ln a. So what is left here? The slope. That is, what will be the slope? Minus ea by r. So that is the slope here. You can compare with the straight line equation and also calculate it. So it will be, slope will be equal to minus ea by r, from which the activation energy can be calculated. So this is graphical method. The next method is from the rate constant we can calculate. So now we are going to calculate it for two different temperatures. So at temperature T1, ln K1 is equal to minus ea by RT1 plus ln a. The same equation that we have used here, we are using it for two different temperatures. So what happens when the temperature is differing? The rate constant will also differ, right? It will become K1 and K2. The temperature will be T1 and T2. So at temperature T1, ln K1 will be equal to minus ea by RT1 plus ln a. A is a constant, so no problem. And at temperature T2, ln K2 will be equal to minus ea by RT2 plus ln a. So now what happens? K1 and K2 are the values of rate constant at temperature T1 and T2 respectively. So now we are going to subtract 2 and 1. So now what happens? ln K2 minus ln K1. Okay. So this 2 we are subtracting, ln K2 minus ln K1. Okay, so now what happens? This is the same. So if we subtract it, that will be cancelled out. Now what happens? ln K2 minus ln K1. So minus ea by RT2 minus of minus ea by RT1. So that is what you are going to get. ln K2, what was ln K2? Minus ea by RT2 minus of minus ea by RT1. Right. So now what happens is minus and minus will become plus, and the minus will be here. So you can generally write it as ea by RT1 minus ea by RT2. So this will be the positive one and this will be the negative one. So we can write it as ea by RT1 minus ea by RT2. So with that is shown here. So now again we have studied this. ln a minus ln b is what? Ln a divided by b. ln a minus ln b is ln a by b. So ln K2 minus ln K1 will be ln K2 by K1, right? ln K2 by K1. So now what we are going to do? Yes, ea by r is common here. ea by RT1, ea by RT2. Okay, it's just that T1 and T2 is changing. ea by r is a constant here. So we take out the ea by r, and what will be inside the bracket? 1 by T1 minus 1 by T2. So now this is in ln terms. We have to convert it into log. We have already studied that. What do we do? Yes, multiplied by 2.303. Okay, so the equation becomes log K2 by K1 will be equal to ea by 2.303 r 1 by T1 minus 1 T1 by T2. So now we are going to take the LCM here. T2 will go here, T1 will go here. So what will happen? The equation will become log K2 by K1 will be EA by 2.303 or T2 minus T1 by T1 T2. So if you have to calculate the activation energy for a reaction, okay, if you know the rate constant for two different temperatures, you can directly use this equation. So that is log K2 by K1 will be equal to EA by 2.303 R into T2 minus T1 by T1 T2. So this equation is also important. So from this also you can calculate the activation energy. So in today's session we have discussed what is the temperature dependence on rate of the reaction. We studied one important equation, that is Arrhenius equation, and in which all methods we are able to calculate it. So I hope the topics for today are clear. So in the next session we are going to study effect of catalyst and collision theory of chemical reactions, by which we will come to an end of this chapter. So I hope what and all we have discussed in this session is clear for you. So that's all for today. Thank you.